All right, so hey everybody, it just occurred to me that I didn't specifically announce that we were going to have a Google Meet class session today. And there's really only one thing that I wanted to talk about. It's the only thing missing from the homework assignment that we didn't cover on Tuesday. So I'm going to try a little different thing here. I'm going to try to use a webcam to do some regular lecturing because of this. So the big question we have today, and I hope this is the right side up for y'all. The big question I have for today is we have this big square, a set of all languages. And in this set of all languages, we've had our regular languages in the middle that had DFAs that accepted it. Now, in the past, we've been able to figure out whether or not a language is regular, such as even, by asking ourselves, can there be a DFA that accepts this? Now, the DFA that accepts it proves that it is a member of the set of regular languages. Today, I'm going to be briefly talking about, and once again, this is going to be posted on YouTube, so no worries there. We're going to be talking about this set here, the context-free languages. Now, we have now seen push-down automata, and we have seen context-free grammars. So when we have a language here, like A to the N, B to the N, we know that it is context-free because we can build a PDA that accepts it. It's how we prove set membership. So if I want to prove it real quick, let's go ahead and do it just because I like to practice. We have an initial state. We push on that bottom of the stack marker that I like to use when I can't figure anything else out. Then we have another state, and this state is going to read in A's. And this is a great example because it shows you exactly what that stack is used for. We're going to use the stack and a hash sign to count so that we can match up and make sure that everything fits. So we're going to go across, use our non-determinism here, and go to another state. And this state is going to do the opposite of what Q1 does, or not opposite, the counter of that. And it's going to read in B's, and it's going to pop those hashes, and it's going to push on nothing. And then finally, a PDA accepts when it has both an empty stack and the end of the input string. This PDA proves that we have a regular language. We also have another mechanism for proving that it's a regular language, and that is the context-free grammar. So let's look. If we have a starting non-terminal and we had the language A to the N, B to the N, we use the non-terminals, A, S, B, or empty string. Now let's see how this works. We have a starting non-terminal, and when we think about string generation, and S, we go from left to right, and S can give us the non-terminal S, but surrounded by the terminals A and B. So we come down, and it is A, S, B. And that same non-terminal S can come down and give us A, S, B, and this would be a bigger S. These A's come down, and this non-terminal S, it'll eventually terminate here. This is what counts. It looks like a nice little Christmas tree, right? But the center is going to be this non-terminal S that's going to help us match up to keep count. And this is very important. These two observations to make. Here, the stack between pushes and pops. Push, pop, push, pop. And now you want ice cream. But anyway, we have this stack that's helping us match. Here, we have the non-terminals that are helping us match A's and B's, A's and B's. It's what we have as our mechanism for it. So this proves that it is a context-free language. But here's the thing. A to the N, B to the N, we drew here. Now, why did we draw it here? Even is a context-free language too, because hey, I can build a PDA or a context-free grammar that accepts even number of A's. And in fact, it's a good practice. Go ahead and try to practice the context-free grammar and the PDA for even number of A's. Now, the PDA is just ridiculously easy. We don't have to actually do that stuff. Remember, it's all we do is we don't use the stack. So A and then nothing, all right? Then A and then nothing. It's actually pretty hard to get it to work for a context-free grammar, though. So definitely practice that. Try to do even A's with a context-free grammar. That's a good practice for you, all right? So now we get to the point of today's lecture, okay? So we knew that even is a context-free language because it's in the set, this large circle of context-free languages. But we also knew that it was a regular language because it's in the set of regular languages, that smaller circle. But A to the N, B to the N is different. We proved that it is context-free. We double proved that it is context-free. And now we're wondering, where do we draw it in this chart? And we have to look at this and go, okay, well, we built a PDA, so it is a context-free language. But it is not a regular language. How do we prove that? The pumping lemma. All right, that's how we knew. That gave us set exclusion. So now we have our big question today. The question today is there a language that is not context-free? That's our big question today. Is there a language that is not context-free? Well, let's think about this. Let's see if we can come up with one. I'm never going to forget that it was Tony that brought up, what is it that makes a regular language know? How do we know? What's our big hint that it is not a regular language? And it's that it needs memory, that it needs a variable. But here's the problem I have. How many things can S keep track of in our context-free grammar? S has something in A and a B. It seems like it can only keep count of one thing. The stack seems like it can only keep count of one thing. And this is going to be our big hint on letting us know whether something is context-free or not. So I'm going to propose a language. And I want you to think, and I really, really, really want you to think about this and think about what can make this possibly not context-free. I'm going to propose a language L containing W such that W is A to the N, B to the N, and here's the kicker, C to the N. Now this is a different language because it added C to the N, all right? So let's think about what this would do. Well, this seems like I can build a context-free grammar that accepts it. Check this out. A starting non-terminal goes to A, B, S, and C, or empty string. So it's basically the same as A to the N, B to the N. Shoot, did I accidentally prove that this is context-free? Well, let's check it out. We generate some strings by starting with our starting non-terminal, and we go from left to right. S goes to A, B, S, then C. Then S goes to A, B, then S, and then C. And then we can let it terminate. Let's figure out what string this is. This is A, sorry. This is A, B, C, C. That's not in the language L. See, the A's have to be, it needs to be A, B, C, C. This didn't work. It put the A's and the B's out of order because it didn't work at all. The same thing would be true if we did it like this. S is A, S, B, and C. For the same reason, S is going to come down. It's going to give us an A, then an S, then a B, and then a C. And the same thing here. We're going to get A, B, C, B, C, which is not in the language. That's not good. Okay, well, what does it mean when we fail? Nothing. It could be that we're just bad at writing context-free grammars. So this A to the N, B to the N, C to the N, we're still not giving up. I'm trying to prove that this is context-free. In order to prove that something's context-free, we need to build a PDA or a CFG that accepts it. We have to figure this out. CFG, I couldn't get it to work. The PDA, let's think about it. We start off here with Q0. We can put our empty the stack, bottom of the stack marker, right here. All right. I'm going to call this one A's, this one B's, and this one C's. This will go to our final state here, where we have our bottom of stack marker coming off. Let's use non-determinism, same way, to move them over. And now let's think about what this stack is limited by. A's is going to count the number of A's. I don't see another way to do this. We have to read in A's. There's nothing on the stack, and we have to pop something or push something. Push something. And then we have to make sure that the B's are equal to the number of A's. The only way that we can do this is we can read in a B, but we have to pop that @ sign. Well, then how are we going to count the C's? Because let's say we have A, B, B, C, C. We read in A, and it puts in an @ then it puts in an @ then the B pops it off, and the B pops it off, and then we're just going to be reading in C's. We don't have anything to count. We have an empty stack. So how do we solve this? Okay, I've got some ideas. Instead of just one @ sign, let's put 2 @ signs. And that seems like it'll work. A, B, B, C, C. It reads the first A, and it pops and pushes an @ and an @. Then it reads the second A, and it pushes an @ and an @. We read the B, it pops an @. We read a B, it pops an @. We read a C, it pops an @. We read a C, it pops an @. That's great, except for if we tried it with this string, A, B, C, C, C. This should not be accepted, but we read the A, we push an @ read the A, push an @ read the A, push an @ I'm sorry. For every A, we would push 2 ats. Now we go to the B, we pop an @ we read the C, we pop an @ pop an @ pop an @ This string is accepted by this PDA. That means this PDA doesn't accept A to the N, B to the N. Well, let's say, okay, well, maybe we can change this. So this can be C's. We're going to push a pound sign to be C's, and we'll use the stack to match that up. Okay, so that's going to be our change. Except for when we look at A, B, B, C, C, we read in the first A, and we push an @ and then a hash. We read in the second A, and we do an @ and then a hash. We read in the B, oh shoot, the order of the stack is all wrong. So this can't be done. I can't solve this. In fact, L, that is A to the N, B to the N, C to the N for N greater than or equal to 0, is not a member of the context-free languages. It is not. How are we going to prove this? Well, we didn't prove it yet because we just haven't. We need a thing. In fact, we're going to need something called the pumping lemma.
Fuck, man.
For context-free languages. That's what we're going to have to do next to prove this. Because remember, not being able to doesn't prove anything. But I am telling you this. I'm telling you that the language A to the N, B to the N, C to the N is not context-free. because we're going to fail. Now, we're still a couple of videos away from being able to show that beyond a shadow of doubt, proving that A to the N, B to the N, C to the N is not context free. However, the thing is, you need to understand this for two reasons. First, there's a homework assignment. Chapter 2.22, I think, is the one where it talks about show that the intersection of two languages is. Take this as a given when you approach problem 2.22. I'm allowing you to say, as Dr. Burris stated in his lecture, the language A to the N, B to the N, C to the N is not regular. You can totally do that, all right? You'll need that for 2.22. The other reason that I wanted to show you that today is that I wanted you to be aware of what the limitations of this stack were, because it helps you understand the power of the stack as well. I wanted you to understand the limitations of these context-free grammars, because the limitation also helps you solve some easier versions, such as A to the N, B to the N. We can do this because it has it's matching up just those two things. It's one variable that's going to be destroyed whenever you have to use it. So this is the important point of today's lecture, is that these non-terminals can match or count just one thing. This stack can match or count just one thing. And this is how they're used. So I'm going to stop. Are there any questions? You can feel free to unmute or put in the chat.
So we can't use a B as a variable in addition to the A for context free? Like if we wanted to represent another piece as a variable?
Hey, Aaron, I'm sorry about that. Can you ask me one more time?
Oh, I was just wondering, can we use another variable in addition to S? Like if we wanted to use a Z and then give Z some rules for context free? Yeah, that looks right. And then you can give A some rules and then B some rules. I can't hear you. I don't know if your mic is muted, I think.
Oh, gotcha. All right. So I'm sorry. That was my fault. I can't say enough how much this question makes me happy. It is a really, really good question to have, because it is another possible solution. It is going to fail, but once again, it is so crucial to see this. This is how Aaron wanted to set up the second variable. So essentially, you're going to be counting A's and B's and C's. And that's outstanding. In fact, we're going to see something pretty similar to this in a future homework assignment, possibly, or a test question. And there's hopefully going to be some rules for A and rules for B that we're going to approach later. But instead, I want to do a preview of what it might look like to generate these strings. Whenever S has a production, it's going to give us some number of A's, or a single A, I'm sorry, by this.
Hey, I got one more question that I'll pull you on there. So what if that second B was just an A? Can you use multiple instances of capital A's rules?
Absolutely. Definitely can. All right.
Yeah,
so
that's cool. You got it. All right.
Okay.
We're good.
All right. So with this, the problem I see is, so let's say that A counts A's and B's, and B counts B's and C's. The problem is that this is going to get like out of whack pretty quick, because see, A can keep on matching A's and B's, and then end up here, and B can just end up in an empty string. In this case, you have A, B, 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 and then a C. The problem is this non-terminal, this A can only match what's to the left and right, and B can only do what's left to the right. There's no connection between these two variables. So when we count the number of A's, we're adding those up. Then the number of B's can only be matched to those A's through A. C can't be that. Now the other question is, can we just use another A? Yeah, we could, but we're going to essentially have the same problem, because even though it's a different non-terminal, they're still not going to have the connection to each other. So if we go, S goes to A, B, A, C, well then, knowing that we have A, and A can either give us A's and B's, or it can give us B's and C's. Or this is actually not substantially better than the previous version, because we go to S and we have the same problem. A, B, or B, A, C. And then from this point on, there's no connection between these two A's. This one can iterate just as many times as it wants to. And this one can just terminate. And this would give us A, B, 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 C, C, C. And it would generate that string, which is not what we want to do. So, yeah, it's a good option, but the problem is that through observation, these two non-terminals, they just can't be connected. They can't keep up with each other. Very good question. Any other questions?
That one covered me.
All right, so I have a challenge that I would like for y'all to do for practice, just as we're getting in. Now, this was part of the homework assignment, I believe. I just can't remember if I assigned it or not. We've seen the PDA for palindrome, and we have not seen the context-free grammar for palindrome. I want us to, just as a point of practice, if you're taking notes, definitely do this for me. Try to draw the PDA for palindrome really quick in your mind, or at least on some scratch paper, or at least on your mind. Try to draw the PDA for it. I'll do the same so you don't have to really worry about it. Push on our bottom of the stack marker. The beauty of this example is it's not counting, it's matching. It uses a stack in a slightly different way. And this Q1 and this Q2 are doing drastically different things. Now, Dr. Paulo already covered this example, and he did so with a huge amount of detail, and also showed how to check this. So if you haven't seen that YouTube video, please, please, please check it out, because he's going to explain a lot better than I did. The way it works is when we read A's, we want to use the stack to record that it's an A. When we read B's, we want to use the stack to record that it's B's. And over here, we're going to do the exact opposite, that when we see an A, we pop an at and push nothing. When we see a B, we pop a hash and do nothing. All right, so that was it. I mean, you look at something like A, B, 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 A, right? This is going to push on in the middle part of the string. It's going to push on an at, and a hash, and then a hash. And then the second half, it's going to read a B, and it's going to pop a hash, and pop an at. So that's how that kind of used to match. But here's the thing. Context-free grammar for palindrome is tougher. It's a little bit harder to think of. And since it's kind of a weird thing to do online, I am going to push ahead and kind of go a little bit my own direction instead of like waiting for people to answer questions. And in this case, I'm going to look for a possible solution, just talking it out. I want to start with A to the N, B to the N. I'm going to put it off to the side here. All right, I just want to put that rule off to the side. So I've got it there with me as an example if I need an example. Trying to understand this problem. A, B, 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 A, B, A, B. I'm looking for a pattern, but I'm also looking just like A to the N, B to the N, where we had like A, B, B, like we were looking in the middle. Same middle things going on here. So there's this reason why I love this example, because this example can give us a little bit of intuition when it comes to context-free grammars. Context-free grammars, in my opinion, are a little bit harder than PDAs, because PDAs are a little bit more like NFAs. So for this example, I'm going to think of something like going from the bottom up. Now, before we had like top down, that was called generation. But we're going to look at the pop from the bottom up, and that's parsing. And I'm going to use this example right here. B, A, B. And I'm going to use this example to think about how I can use the same thing as A to the N, B to the N to match things up. Since it's in the middle, let's do this. Let's put an empty string right here and say that's going to S. And we want to keep going up until we have a single non-terminal. So when I look at it this way, I get this weird ability. I can go S goes to, well, I know it can go to empty string, but S can also go to, see how I'm building my Christmas tree in reverse? This would be S, and this would go down to empty string. I'm building my Christmas tree from the bottom up. So I know that S can go to A, S, A. Not only that, but I know that S can go to B, S, B. And y'all, that's the answer. That is the answer for how to build it out. Oh, yeah, I want to see yours. Copy it. Oh, okay, that's awesome. Good job, Brandon. I tell you what, go get some 99-cent cheese sticks at Sonic today. No coronavirus in the pickup window, so you'll be all right. All right. That's a little bit of intuition on how to build these context-free grammars. Kind of build the Christmas tree, but from the bottom up instead of the top down. That way it doesn't take all of this ridiculous amount of intuition to build out. Are there any questions that you have about this one particular example, palindromes? Nope. Brief mention about 2.22. I already said this a little bit. It's asking for the language M, which is A to the N, B to the N, sorry, no comma there, C to the M, or N and M greater than or equal to 0. And for the language N, which is A to the M, B to the N, C to the N, or N and M are greater than or equal to 0, is this context free? Yes. I can build a context free grammar that accepts it. M goes to F.
Hey, Dr. Beers,
Hit me.
I sent you an email and asked you about 2.2. You said 2.4 instead of 2.2.
So I think this is 2.22. Yeah, so the homework assignment has 2.4 and 2.5. So it goes, I think, 2.1, 2.4, A through F, 2.5, A through F. And I think that there was an email about that getting changed to the class as well. But there's another problem. It's the one that's actually in the problems and not the exercises. Part of it,
Yeah.
that's the question. If M and M are both context free, is the intersection of M and N context free?
That's 2 point, looks like 2.2 from the exercises. I'm looking at 2.22 right now, and it's let C equal X hashtag Y such that XY is included in 0 ones to the star, and X and Y are not equal to each other. Show that C is a context free grammar.
All right, let me see which one it is real quick. So I came to Hammond today to get some of that good internet for today's class, and that's what it is.
Yeah, I was wondering. I started doing I've already done 2.4. That's why I was making sure that's the one that you wanted.
So it's 2.18. No, it isn't. Maybe it's an earlier one. It is 2.2a, and that is not assigned. I'm sorry.
Yeah, I think
You
wrote it. You wrote it on the original one, but then you said do A through F, and then I was asking you about it, and you said not 2.2. You said
yeah.
do
So
2.
I meant to have 2.2a and then 2.4 A through F, but I already changed it. So I'll just show you what the answer is then if it's not there. I thought that was included in the assignment still. So I'll just go ahead and show you the answer anyway. So this M is definitely context free. Now they use A and B or whatever, but that's fine. So I can do it like this. A to the M, B to the N. It means that S needs to count A's and B's, but the C's can be just anything. All right. So let me see. I'm going to use a different non-term here. So I'm going to use A here. So A can go to A, B, or empty string, and this will make sure that's A to the N, B to the N right there. And then C can give us any number of C's, which is what this is. N is the same thing, but it counts the second part. N goes to S, S goes to A, and we'll call this one a capital A, then B, capital C, and C. So A would go to just any number of A's, and C would count our B's and C's. All right. So this shows that M is context free and N is context free. So I'm going to open it up to the class now. Is M intersect N context free? What are y'all's thoughts on this? Is M intersect N context free?
They would both have to be. They would both have to be context free for the intersection of it to be context free.
M is context free. Here's the context free grammar for it. N is context free because here's a context free grammar for it. And here's the thing: is M union N context free? Yes, it definitely is. All we need is a starting non-terminal that goes to M or N. So yes, that one is. But here's the question: is intersect context free? Well, we only know of one language that's not context free, and that's A to the N, B to the N, C to the N. I'm telling you to just believe me. We tried it and we failed. That's going to be our context free language. So, can anybody think about why this might not be context free? $0.99 cheese sticks. All right. Here's my answer to this. M is A to the N, B to the N, C to the M. N is A to the M, B to the N, C to the N. This means there's a set of strings for M. They are A, B, C, but they're also A, B, C, C, A, B, C, C, C. It's also A, A, B, B, C, C, but also A, A, B, B, C, or A, A, B, B, C, C, C. And then there's a nice dot, dot, dot here. Those are the strings that are in M. There's no relationship between the number of C's and the number of A's. There's no relationship between the number of C's and the number of B's in M. So N, we have like kind of the opposite. ABC is in N too, but ABCC is not. You could have AABC. You could have AAABC. You could also have AABBCC because it's N would be equal to 2 and M would be equal to 2. But you could also have ABBCC, or you could have AAABBCC. The number of A's has no relationship between the number of B's. The number of A's has no relationship between the number of C's. So the question is what is the intersect of those two sets? And I mean, really, just check them. The intersect is if it is in both of these sets, is also an intersection. Is ABC a member of M? Yep. Is it a member of N? Yep. So A, B, C is a member of M intersect N. ABCC is not a part of N. ABC is not a part of M, even though it's a part of N. The next string that I see that is in both places is right here, AABBCC. And I'm going to go ahead and put some dots. I'm going to let this sink in for just a second. When M is A to the N, B to the N, C to the M, and N is A to the M, B to the N, C to the N, what is M intersect N? The answer is A to the N, B to the N, C to the N. The only time the members of N will also be in M is when the number of B's is equal to the number of A's. And in that case, the number of B's is also equal to the number of C's. The only time a member of M is when the number of C's is going to equal the number of B's, right? If N is going to have something that's shared with M, then the B's and the C's have to be equal. Well, that means the A's and the B's also have to be equal. So the intersection of M and N is A to the N, B to the N, and C to the N. Why do I love this question so much? because I want to be absolutely clear. This is not part of some 257 discrete structures, set theory. This isn't a set identity, right? It's not like De Morgan's theorem. Or De Morgan's law, I'm sorry. It is just a matter of observation. It's what we have to think of when we're thinking of languages. And I love that the intersection, the only way a string can be a member of both M and N is if A, B, and C are equal. This proves that the intersection is not one of the operations that the set of context-free languages is closed under. It is not. So a context-free language that is intersected with a context-free language is not necessarily context-free. To prove this was really, really easy. But to disprove this, I would argue it's just about as easy. But it's just this observation of what sets are, how that set knowledge of sets can help you. Are there any questions? All right, so that's a lot for today. I'm going to be available on Google Chat all day tomorrow as you're finishing your homework assignments. I'm going to be putting up a submission link like right now to post where you can push them in. Look, I'm going to be as lenient as possible. However you can get it solved, whether it's Google Docs or whatever else, just get it submitted. Draw.io is fine. Scanned papers is fine. It's a little bit hard for me to read pictures. So if you have a bunch of pictures of your homework assignment, do copy and paste those pictures into a Word file so I can at least see them together. But once again, I'd really rather it not be pictures for everything. It's really hard for me to grade because I can't really see what's going on very well. But that'll be submitted. And I'll be available all day through Google Chat. You'll access that through your email for Southeastern on the bottom left-hand side, and you just start a Google Hangout, and you can select recipients, and it'll select me. Just put in Jay Burris, and I should be able to get it. All right. If y'all don't talk to y'all again, y'all have a great weekend.
All right. Hey, Dr. Burris.
Hit me.
Hey, can I ask you real quick? Could you do a PDA for just like something random? Because like I've seen that example. I've seen that example for palindrome. Could you just do a random like PDA, like even, or no, not even, because that's easy. Like starts with 1 and ends with 0, maybe. Just so I can see how you run through the process real quick, because it's like catching me up.
Let me think of an example real quick. Oh, this is a good one. This one's really, really hard. Do you want a hard example?
It doesn't have to be hard.
Oh, okay then. All right, let me think of something that won't be as difficult then. Give me a second. Let's do for the language L, where it's A to the N, B to the M, and N is equal I'm sorry, 2n is equal to m. So
Are you screen sharing?
is it not showing?
No, there's no presentation.
Huh. All right, so it should definitely be up, I hope. You click people and go over to John. It's it's still the whiteboard.
Uh-uh.
Ugh. So I can still see it here. Can somebody in chat, like Sajan or Usaf or Barack, can y'all tell me if y'all can see the screen?
Yeah, I can see the screen, like the screen.
Yeah, I can see it. It's on the bottom left corner,
Oh, I don't know.
but I can see it.
All right. So hey, Aaron, real quick, if you can click on your main screen and do the three dots and go to settings. I'm sorry, not settings. Change layout. You can select spotlight or sidebar. I would recommend using sidebar, and that way it can give you the larger screen. And then you can select my picture, and it should bring it up really, really large.
Okay.
Can you see it?
Yes, sir.
Awesome. All right. So to be clear about what it is, so if m is equal to 1, that means n is equal to 2. If m is equal to 2, then that means n is equal to 4, so on and so forth. This means that it looks like this. The language is A, B, B, A, B, 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 and then A, and then 6 B's. That's the language that we're dealing with. So immediately, my first thought is when I'm building a PDA, and it sounds crazy, but it's just like programming. I like a step one, man. It's just, I like to have this bottom of the stack marker because it gives me a starting point. And I will literally write this out with my $sign right here to make sure that I know where I'm going. All right. So my question with this is essentially the same as asking, what am I counting? What am I matching? What is this stack going to do for me? That's where I'm going to think for just a minute about where I'm going with this. All right, so I'm going to be thinking about this. For every A, I need to pop 2 B's or something. How can I figure this out? One thing I know for sure is that I'm matching A's to B's, A's to B's. So I'm going to do what I know for right now. And every time I read in an A, I'm sorry. Every time I read in an A, I'm going to push on a hash. And I'm going to use this as my example string to try to figure out what the heck to do with that hash. So I'm going to come in, I'm going to push the bottom of the stack marker. Then I'm going to loop twice. I'm going to read in the A. I'm going to read in the A. And now's the part where we got to figure it out. If we were doing this like A to the N, B to the N, we know now after we've read the A's that Q1 is counting the A's. We need to go over to Q2 with nothing and think about what Q2 is going to solve. And once Q2 solves it, we can get to a final state by popping off that $sign. But we have to figure out how to count this. See, the problem is I can't just do a loop and make it to where it reads in a B and it pops off a hash because there's not enough of them. We don't have enough hashes to count. We need to go this, like we need to do 2 of them. So how can I use the stack to force, essentially doubles here? I'm going to give you a hint. What if we read in a B and read in a B? Now this is our even, right? How can we use this loop to say for every A that we read, we pushed on a hash? For every 2 B's, we're going to pop a hash. But we aren't going to need to push anything. I don't think we need to do that. So let's just put empty strings here. So we came in $. We pushed 2 hashes. We come over here. We have 4 B's. Well, if we have a B and a hash, we can go down to Q3. Now, we don't want to put a hash right there because that would take 2 hashes. We only have 2 total. We're going to need 4 of these suckers. But if I put it here, in that first hash, this is how we can make it to where we're going to, read 2 B's, but only pop 1 hash. So that's kind of how I solved it. It's all about trying to figure out, and just like context-free grammars, if this were the same way for a context-free grammar, I would think A, B, 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 and I would work from the top up. Man, I would just do empty string up to S, up to S. I would do my Christmas tree. That's how I solve these things. I would design this PDA in the same way, where I'm sitting here trying to think about, well, what do I have to put where for this to work, right? And that's what that's doing there. Is that an okay example for you, Aaron?
Yes, sir. That was good.
Awesome. All right. With that, I'm going to go ahead and call the class for today. This is being recorded. I'm about to hit stop recording, and for some reason, it is getting shared at other people's drives. So let me see.
Yeah, I saw that the other day.
So, Sejan, can you hear me okay?
Yeah, I have one more question though.
Oh, okay.
Yeah, my Google Drive's not even updating for some reason. Like I'm not getting any videos.
Oh, that's crazy.
Yeah.
All right, so Sejan, what was your answer? Question?
Yeah, I mean, like, do we have to show PDA every time to prove if the language is context free?
No, you can use a DFA.
Mm-hmm.
If you prove that it's regular, it's also context free.
The way you saw us in the video, like using that brands, you mean the Christmas tree, the way, so we can use just that way, or we need to show the PDA?
Either one. So one of the things that I'm cutting from this class, because of this online stuff, is that the equivalence of PDAs and context-free grammars, I'm only going to very briefly show one of the translation methods for that. I'm not going to show it. So if you create a CFG for a language, that does prove that it's context-free language. So if you can build the Christmas tree, then you can prove that it's context-free.
Sounds good.
All right, so Sujan, when I hit stop recording, it's going to save a copy to your Google Drive. I desperately need you to share that with me.